Welcome to Horn Online Training, Training Module 2.2, Supermini and Mini Geometries. I'm Edwin Tunney, Training and Technical Specialist for Horn USA Incorporated. Today's topic covers not only the micro geometry of Supermini and Mini tools, but also the macro geometry. So there are similar options for Supermini and Mini. So you can kind of take what we're doing here on the Supermini and apply it on the Mini side of things. If you look into all the systems, you will find that we have boring tools with 18 degrees, and that's off the back side here. We have 47-degree tools, 10-degree tools, 45-degree back boring tools, and 18-degree tools, so back clearance of 18, and the front side 90. And then also pre-part off and chamfer. Of course, we also have grooving tools. Those are not discussed in this training because they're pretty self-explanatory with respect to geometry. So as you may know, the Horn tools, they're very specific, so they don't, in the Supermini and Mini systems, they don't follow an ISO format. So I thought it was a good idea to break down the ISO part number and make that a little easier to understand. So in R105.1823, what does that mean? Well, the 18 is essentially alluding to this back clearance on the insert. The overall actual clearance is 21 degrees, but the recommended sort of angle of the part should be 18. The front side usually is 8 on these boring tools. The second part of that number is 2.3, and what that means is 2.3 F dimension. So the dimension from the center line of the part to the tip of the tool, that's the F, and that is 2.3 millimeter. It doesn't always follow that exactly, but in general, that's the dimension you'll have. You look at another example of 4723, so an R105 4723, that is 47. You actually have 48 degrees if you look at the A drawings or the dimensional drawings in the catalog. And then 23 also is the F dimension, or 91 thousandths. So 2.3 millimeter or 91 thousandths. 1023, so you have a 10-degree clearance. These are reinforced tools, so these are designed for a little heavier boring. Because you have less clearance, you have the ability to have a little bit stronger neck on the tool, so a little bit more stable. And this one actually is 2.3, but the actual dimension is 110 thousandths on the F dimension. So you can see where sometimes that part number diverges a little bit. Then you have tools, the 9023. So this is 90 degrees on the front end. Also 2.3 or 91 thousandths on the back side. If you look at these tools as well, it's sort of 18 degrees behind here, or 21 in actual, but then to have some clearance, you want a few degrees clearance there, so it's actually 18 degrees. A 3023, so a 3023 is on this back boring tool, is the front side here. So the front side of the part is 30. That helps you avoid anything here that's more than 30 degrees. And then also 2.3 on the F dimension. So from the center line to the cutting edge is 2.3 millimeter or 91 thousandths. A note to say here, the 3023, it's 90 degrees on the front here, but it's not recommended to use that for cutting. This is primarily just cutting on the back side of this tool. Would recommend using the 9023 to do front side machining. 45-45, so an R105 with a 45-45 designation. That's an exact, so it's 45 degrees on both sides of the tool. You can use that for profiling when you have an angle here, 45 degree, 30 degree angle. Same situation with the F dimension. It's just not called out in this tool. It's not called out in the part number. Prepart off and chamfer. So this is kind of a unique tool. This is designed to get your component ready to part off, and also put a small chamfer on the inside, whatever that chamfer might be specified. The starting depth for that 45 is specified as T1. So that means you have to groove to at least the T1 depth to start the 45. And then beyond that is the depth that you groove will be, since it's 45 degrees, will be the width of that chamfer. These are really nice tools because they can eliminate some post-part off operations and avoid that you have to pass a tool over in some cases to a second spindle. You can see here the part number is an 08, and what that 8 means is 8 degrees on the part off from the axis of rotation. So it's like an 8-degree part off tool. And then the 10 is the width. So the width is 1 millimeter or 39 thousandths. A little bit more in depth to these tools because they're a little different than others. The pre-part off tool, it should be programmed so that the inside edge is essentially the same, in the same plane as the back of your component. The pre-part off tool program depth will be the T1 value plus the required chamfer width. So if you go, you would add half your bore diameter plus T1 value, and then the depth of the groove would be the width that you need on chamfer on a 45 degree. A note about sort of pre-part off tools and how to use those in conjunction with a part off system. So if you look at the first case here, this is a sharp corner tool at 0 degrees. So at 0 degrees, the sharp corner tool is going to have the weakest cross section if you're using a pre-part off and chamfer tool. So that weak cross section can cause a larger burr. So as this is being parted off, that weak section can make this sort of disconnect sooner than you want it to, and cause a little bit of a burr on the back of the part. The other situation that you can have is when you use an 8 degree that's opposing the 8 degrees on your pre-part off and chamfer tool. The problem here is when you use a bigger radius. So the bigger the radius, the more this burr will rise on the part. So an 8 degree radius is also won't produce the best results. An 8 degree sharp corner and then an 8 degree sharp corner are going to produce the smallest burr on the component and leave you the best finish on the back. The only thing with part off tools, as always, if you have a lead angle like this, an 8 degree lead angle, just be aware that under higher pressure, this tool is going to diverge. It's going to make the surface on the back of your component concave. So you're going to have a dish out right there. So the more aggressive you get with that tool, the higher the force and the more that's going to diverge from a flat plane. So just be aware of that. But best situation is a, a sharp corner tool with an 8-degree lead. All right, so we've talked about the macro geometries. Now let's get into the micro geometries. So you can find geometry on grooving and boring tools in the Mini and the Super Mini systems. So from the 110, 109, 105, the 18P, all the way down to the 108. So there's geometries available. There are two main groups of geometries. You have the standard substrate, the carbide geometries, and then also you have geometries in the ultra hard materials, and we'll talk about both. So if you look at the Super Mini system, you have two geometries available. You have the H and the HV, and though the H is available on the 105 and 110, and the HV is available on the 105 and 109. So the 105 system is by far, if you choose that, if you need to have those geometries, you have both the H and the HV. On the other side of things, the Mini, you have the D and the R. So the D geometry for grooving and the R for profiling. And those are present on the 108 series, the 10P, 111, 11P, 114, 116, and 18P. S is just the insert. It's precision centered. Also on the R, you have it on the 108 all the way to the 18P. So if we look at the sort of the purpose of these geometries, so the H is to provide chip control in very ductile materials in smaller bores. So when you would use that is when the chip breaking is not achieved with the HV. I would highly recommend. We sell parts in 2-part quantities. Whenever it seems a chip breaker is necessary, if you're going to go with a system, try the HV first and then use the H second. And you'll see in a moment the reason for that. Use the HV in ductile materials and apply this really as a first choice. The D geometry, you're going to use this when you need chip control in grooving. The main purpose of this is grooving. You can do side turning as well, and it does produce a chip in side turning. But mainly use this when you have issues with chip packing. The R geometry, when you need to break chips in profiling. So to look in higher detail with the H and the HV, so you have the H geometry. You can see is a very tight and shallow geometry. So the HV is a little more wide and open. So that's why I say start with the HV, and if that's not effective, then switch to the H. What's not thought about sometimes in chip breakers is when rolling this chip, if you're rolling it really tight, it can be damaging to the cutting edge because you're creating a lot of heat and pressure when you're rolling that chip. So if you can get by with the HV is really the better option. Also, don't forget about your depth of cut. If you're cutting below the radius here, you're not really making use of this chip breaker. You have to be sort of over the radius to even activate and use the function of this chip breaker on either the H or the HV. The D and the R geometry. So the D geometry is grooving and side turning. The R is for profiling. The full depth for both the D and the R is not recommended. So you don't want to bury the tool, especially the D. The D is a groover. It can do side turning. That's true, but you don't want to bury it up past this because what will happen is your even if there were cutting edge here, which in some cases, some size of tools there may not be, your chip would just sort of ride on this flat area and it wouldn't get into the chip geometry. The R, the same thing. You do have to have a minimum to take advantage of the R geometry, but don't max this geometry out. It's not a good idea. You're putting a lot of pressure when you do that. So the last thing to talk about is the Supermini geometries for ultra hards. So you'll notice that the Supermini and the Mini both have the same sort of configuration, broad configuration of ultra hards. You have an H0 geometry, an H5, and an HF. You have geometry with that on the 105 system in the Supermini, and on the Mini you have the 107, 108, 111, and 114. So the H0 geometry is really for isogroup N, non-ferrous materials, so aluminums, anything that doesn't contain iron. You can also throw brass in there or copper when you have sort of pure alloys. The H0 really should be used when the maximum edge strength is needed when you have an abrasive material. So if it's really abrasive aluminum, pick the H0. The H5 is similar materials. So you're talking about non-ferrous or isogroup N, but also at longer L2 reach lengths. So when to use that? Use it as a first choice when you have a softer, more ductile material with lower abrasive particles, and further out, if it's extended further out and you need to reduce the pressure. So you can see the H0 is flat. It still has side clearance, of course, but it's a flat orientation. The H5 is a positive, so it's both positive on the rake face, and then you also have clearance on the flank face of the insert. And the last is the HF, so that's bore machining in N group materials. So same material group, but you use this when chip packing is an issue in smaller bores. It's recommended though that the bore is about 50% larger than the tool. So you still want to have some room for this chip breaker. That's sitting at 0 degrees, but because of the geometry, it's going to cut really cleanly and positive, and it's going to roll a tighter chip. All right, that's it for this module on Supermini and Mini geometries. Check back and subscribe to the Horn YouTube page to get further information and watch further videos. Thanks for joining us.